course, you could include all non, a lot of several, a lot of nonlinear transformations of x, because you just don't know which kind of nonlinearity, right? You just estimate linear model, and there are some people in the audience say, maybe it's nonlinear. And if you don't know exactly what kind of nonlinearity, then you can imagine that you can add, I don't know, you can try out so many variants. Nonlinearity, everything, right? So, but you don't want to test, 100 variants, 100 parameters, 100 versions. And the idea of the reset test, the regression specification test, is to run a linear model with OLS, right? And then to include here the squared fitted values of your first stage ordinary square regression. And then re-estimate the model. And you see the idea is that, well, if the square term, for example, of x plays a role in determining y, then gamma should be non-zero. If, however, the model is linear, then we know that this variable here should play no role, that gamma is zero, because this is okay. So actually, the reset specification is much more general than here. So you can, because here's the squared fitted value, so write out on the alternative hypothesis, the nonlinear relationship. You see that this here captures a lot more of nonlinearity, right? So this is not only if the true relationship is a square, right? So it is also if it's cubic or whatever. In any case, the square term here would be so the reset test, so there are more general reset equations, including square terms or interactions or whatever, But anyway, we have only one only work of the first stage. So null hypothesis is gamma 0. In that case, the linear relationship, right? If you add more of these things, you can also use F-tests, right? And this is, easily distributed. Under the null hypothesis, it's just the standard t-test. Okay, so not a thing. All right. So if you look at empirical applications, very often, if there's a risk or if there's a discussion whether the relation is actually might be nonlinear or not, then you show your regression result of a linear model, and then there is in the notes the result of the retest, which hopefully does not reject the null hypothesis, that it's stable. Very stable. Okay. If you have to reject gamma 0, then obviously the relation is nonlinear, and then you have to think about, okay, how to modify my linear model. Okay, that's the reset test. So we know the variables which are relevant, but we don't know the function for it. A second way to talk about instability of a linear model is the so-called Chow's breakpoint test. Chow is a statistician that introduced that kind of test, I guess, already in the 60s or 70s. So it's a very standard, old-school test. What is the idea of that test? The idea is, well, maybe we have a nonlinearity here, but it's not a very complicated linearity in the sense that there might be log, cosine, whatever, right? But it's just that for some values, the coefficient beta changes. So there is some threshold where, for my regressor, where the effect changes. And this is here in this figure, right? You see that for small values, it's like this, for large values, it's like that, right? So obviously, this linear regression is not very, well, it's not the same linear relationship over the whole sample period. Okay? This kind, and you see what happens, right? Here you have a W variable, this is 1, whenever xi is smaller than, for example, x bar. So this could be every value you make, right? You take it, right? So here in that concrete example, it's just the average x bar, right? So you ask here, is my linear relationship between x and and y, does that differ for above average x values relative to below average? So for small and large values, is there a difference, right? So if this is the, I don't know, we had a food expenditure example, right? So this is food expenditure, this is income, right? Is that relationship for people with low income different than for high income? Okay, for example. So, okay, you see, if you multiply this out, like another hypothesis that it's just the linear relationship that the impact of income on food expenditure is beta, whatever income is, then it's just gamma 0, and it's again just a t-test, right? And if you have more, more breaks, then it's just an f-test. If you have more regressors that make break, you have an f-test, right? You have three betas here, beta 1, beta 2, beta 3, then maybe it's just an f-test. So that's the child breakpoint test. And you see this here, this works when you have something in mind that it's non-linear in the sense that it just breaks, the linear relationship breaks at some certain point. That might make sense, right? Very often child breakpoint tests are applied in time series analysis, right? Because what you need for x here is obviously something like a natural ordering, right? So in size or so, right? And that natural ordering is, of course, particularly plausible if you have time series data, right? Because then, obviously, the child breakpoint test, if you order it, if this is just xt, then you say there was a linear relationship until the year 2000 or what, which looks like this, and from 2000 onwards, it's like that, right? Then the slope coefficient changes not because some variable was extraordinarily large or something, but it just changes because of a break point in time. Okay, this is why it's called actually break point test. So I guess the original idea was to apply it to time series analysis. Well, is a relationship before German unification different and after German unification, and so on and so on. Okay. Note that there are, if you go to sophisticated econometric software, you will find more breakpoint tests, especially the so-called quant entry breakpoint test. I just want to say a few words about that. The idea here, or let's talk about that here first. If you apply this here, and if you find a breakpoint, how could you discuss that? What is the problem with that child breakpoint test? Look, my example were always like, there's a German unification, or the introduction of the euro, or there's, I have a story, why the slope coefficient at that point of time, or when some variable, for example, inflation increases above 2% or so, right? And there's some natural threshold, some natural number, some natural time point where it makes sense to ask, well, does the relation changes at that point of time, or when inflation increases 2% or whatever, right? Whenever you have a story like this, whenever the breakpoint is exogenous, right? So if there's some idea, some theory, some literature, some very plausible good reason to test exactly at that point of time, or exactly when xe is below its average, I don't know why that makes sense, right? Then you can apply the child breakpoint test, but you have to defend. Why? Why do you have to defend yourself when you estimate a relationship, a linear relationship? You present a child breakpoint test. Look, I rejected the 5% level. Why do you have to defend that test result? Because when you run a regression, when you have a linear model, it's a perfect linear model, right? In 5% of all cases, you will go up beyond some 95 critical value for the test, right? So look, if you want to test whether the standard deviation of a random variable is larger than 1 or not, right? Then even if it's normally distributed with standard deviation 1, in 5% of your values you will go up, you will exceed some critical values, yeah, because it's a